Okay, so on April 8th, there's going to be a total eclipse. The moon and the sun are going to line up and make a shadow on the earth. Now the shadow is going to cruise across the United States, something like this. The shadow should be approximately 115 miles across. Now let me show you why this is not possible on the heliocentric globe model as we are shown. Here's the best way to do it. Let's make a model. Okay, so here's our 6-inch globe, and I got it tilted like it would be 3 months after the winter solstice. Now down here, 15 feet down, or 30 Earth lengths away, is a golf ball. Now the Earth is a 6-inch globe, which is 8,000 miles across, and the moon is a quarter of the size, which would be 2,000 miles, which would be roughly 1.5 inches, which is real close to a golf ball size, right here. And down here is our sun. All right, so now let's cruise down here and see what our eclipse looks like. Okay, so here's our eclipse. Now the sun is prospectively the same size as the moon. So here's our eclipse right here. And then the moon's going to cruise on by, and the sun's going to pop out again. Let me zoom in and show you a little better this time. Okay, here's our eclipse, and then the moon is going to cruise on by again. Now let's compare our eclipse to some real eclipses. Looks like a match. So let's go back to our model. There's our moon, there's the sun down there. Now let's see what the shadow looks like out on the earth. Shut the light off. Now we're going to come down here and check it out. Now the shadow is way too big. It's covering the whole United States, all of Mexico, half of Canada. The shadow should only be 100 miles wide. It should look something like this. Now, why is the shadow way off? Let's see what NASA has to say about it. Now here's their model of what's going on. Now they're saying that the sun is way bigger than the moon, and it's making an umbra penumbra. So it casts a tiny little shadow on the earth. Now let me show you a real life example of this model. Here's somebody, I think he's trying to create an umbra penumbra, but he's casting a shadow smaller than the object, so we'll give him some credit. And let me show you another one after this one.
This eclipse stick is a scale model of the Earth-Moon system such that the model Earth has a radius of 1.5 inches. The Earth-Moon distance in the model is at the shorter end of its range of values. Using this to demonstrate a total lunar eclipse, we can see that
here she's demonstrating a lunar eclipse. That's not what we're talking about. And here on the solar eclipse, she's very vague.
Demonstrating a solar eclipse allows us to see that the shadow of the moon on the Earth is pretty small. Only those in the umbra of the moon shadow, the gray swatch from Oregon to South Carolina, could see a total solar eclipse. Others, not in the path of totality, will see a partial solar eclipse if they're in the penumbra, or no eclipse at all if they're not in the shadow of the moon.
So here's her solar eclipse model, and it's super vague. It really doesn't even show you how they got it, how they did it. But let me show you what they're not showing you. So I have a roll of tape laying around. Let's cast a shadow with it. So let's jump back here and try to cast the umbra penumbra. Okay, so my light is wider than the roll of tape. See that? Now we're going to lock it here and try to cast the umbra penumbra. Okay, so we got our light. Here's our tape casting the shadow. And we have our umbra penumbra right here. Okay, now let's see what it looks like prospectively from here. Okay, so here's our eclipse from back here. You see how the light sticks out on either side? And that's how you get your umbra penumbra. Let's put our eclipse and our shadow side by side so you can see what's going on. Okay, so notice how on the eclipse you can see light on each side of the tape. And that's what causes the umbra penumbra right here. The skinny part is smaller than the object that's casting it. Now let's look at the eclipse on the top and the bottom. there is no extra light hanging past the tape. So there is no umbra penumbra on the up and down side of it.
In other words, in order to have an umbra penumbra, you have to have a light that's prospectively larger than the object that's casting the shadow.
So in order to have an umbra penumbra, prospectively, the sun would have to be bigger than the moon. Well, if the sun was bigger than the moon, you wouldn't have a total eclipse. That means the umbra penumbra is not possible, and they're obviously incorrect about the size of the moon. I know what some of you are going to say. Look at this drawing. Look how big the sun is. Look how small the moon is. Obviously, that's how it works. Well, real life isn't a drawing. If something's prospectively smaller, then it's actually smaller. Let me give you an example. Okay, here's a light. Now, if I put my finger here, this light is going to light up both sides of my finger. Now, across the lake is a street light that's way bigger than the light I just showed you. Now, with my finger, I can block that light. Guess what? It's not going to light up both sides of my finger. I don't care how bright it is. That's because prospectively it's smaller. That makes it smaller. You can't draw it bigger and then all of a sudden the light's bigger and brighter, right? Hey, let's draw it. Here you go. I got a 16-inch street light a mile away. Oh, here's my finger. Okay, let's draw diagonal lines. Oh yeah, look at my finger lights up on both sides. That's ridiculous. Real life is not a drawing. Here we are back at the lake. I can block out a whole house with my finger, let alone a street light. Let me show you another example. Now here's the light 3 times bigger than the globe. Now here's the corner right here. Now you can see around the corner, see? That's because the light is 3 times bigger than the earth or the globe or the ball, so you can see around the corner. Now let's come down here. Now there's a solid equator line. Even though the light's bigger, because it's farther away, it's prospectively smaller. It can't shine around the corner. It's prospectively smaller, that means it is smaller. So as it sits, our eclipse model shows to be correct. That means the shadow on the earth would be too big. So the moon, as stated in the globe model, is incorrect. The size is incorrect, or the distance is incorrect, or both. So the shadow on the earth is 60% bigger than the golf ball. So that means if the shadow on the earth is only 100 miles wide, then that means the moon can only be around 30 to 70 miles in diameter, which is way off from 2,000 miles in diameter. And another thing, how do we even know it's the moon? Like, here's a 2017 eclipse. Do you see the moon anywhere? Something's blocking the sun, but do you see the moon anywhere? You think during the day, when a clear sky like this, you would see the moon, right? You'd think you would see the moon in the sky and then it slide over and make an eclipse. Here's another video of the 2017 eclipse. Now let's stop it right here. So the eclipse is happening right now. I don't see the moon. Do you see the moon? The sky looks pretty clear. I don't see the moon. Let's continue. Now when you look through the lens, the moon, the sun is already being eclipsed. I mean, technically, how do we even know this is the moon that's doing this? How do we know it's the moon?
This is absolutely insane. I feel like it's hard to breathe.
How do we know it's the moon? Is it even the moon?
Oh my god.